Hello? I'm here. Okay, perfect. So, well, we're going to start with the talk. The topic is how to fool an ADC, right? It's basically about hardware, attacking hardware devices. So, the talk, I'm co-speaker with Alexander Bosep that he didn't manage to come, but it's a work between the both of us. A bit of introduction. We both work at the hardware lab we have in Madrid. Active has in Madrid. Alexander was a security consultant, and we both work in we are expertise in embedded devices and hardware hacking. So those are all details. In case you want to contact us anytime, Twitter or email, that's fine. So this is a bit what I'm going to talk today. Since this is about how to attack embedded systems from a pure analog point of view, we have to study how the ADCs actually work. So I will spend a bit of introduction explaining how these devices actually work, which are their features, how to interface with them, and then we'll move to the actual attacks with the system. So, how many of you do already know what an ADC is? Just a bit of survey. Okay, perfect, great. And how many of you have already programmed systems with ADCs, like interfacing with them? All right, perfect. That's great. So I'm going to start like a more general introduction. An ADC is the part of it's a hardware component that helps the digital system interact with the analog world, right? Basically, it's a passive system where you can read all the signals. They help you translate what the actual voltages or the actual measurements are. If you want to, for example, read the temperature or current or voltage, this system helps you translate the actual signal into values that can be used in a digital system. So it helps you translate into the floating point number that you can then operate with that in a digital manner. These usually are characterized between different things. For example, the bandwidth is the type, how much frequency they can actually read. The signal noise ratio is also important. Also the sampling rate and all these things are parameters that someone has to choose when they're working with them. There are different types of ADCs. These are the more common ones. The SAR, the sigma delta, the pipeline. They are here like they are grouped into which are the conversion rates that they usually work. So just a simple thing. So how this ADC work, right? So basically, when we have an analog signal that we want to read, we want to know exactly at a certain point of the time which value is there. Because if we are sampling, for example, the temperature, you want to know exactly which is the value on that channel at a specific time. So this basically has a very rough approximation in a point that you want to read. Just you call the ADC, it gives you a value, and you keep that value for a while. And then the next time you want to read the value, you go back, you ask for another value, and he will probably give you the most recent value from the analog signal itself. This is like how an ADC looks like from a functional block point of view. This is an example for the AD7812. It's a very common ADC. It's a SAR ADC. But what is inside doesn't really matter right now. I just wanted to point out how they usually work. They have two main interfaces. The left one is the one that is hooked to the analog world. Those are called channels. So this specific ADC has 8 channels that we can plug signals or systems or anything that we want to measure. If we are in a RF environment, we can probably plug the signal read from an antenna or the temperature, all the voltages that we want to track around the system if we're in a monitoring device. And the part on the right is the one that is hooked to the serial port, is the interface with the host device, which is the one that actually needs these values to process something. Let's say if we are sampling which are the voltages of a system because we want to make sure that everything is working okay, and we want to keep it in control, we will read in the channels and say, okay, the voltage for the conversion type is okay. The voltage for the motor is fine. The voltage for the channel that controls the boiler is fine. So we can sample those values and see what is going on. This is how it looks like in a real world. It's a chip. In this specific package, we have there the SPI pins, all the other channels. So it's like you can have an idea how these things look like. This is the way these ADCs help us read what is in the analog world. It's basically like it's summarized in this slide. So we basically have a voltage reference, which helps the system decide which is the maximum value we can get in amplitude, right? So for example, and also describes each bit, because we are gonna, at the end of the day, since we're interfacing with we want a digital data, we're gonna get a bit stream, right? Like let's say if the ADC has a precision of 12 bits, we're gonna get 12 bits worth of data. So each bit has a meaning. So with this calculation, once we read the whole number, we can do a simple calculation and get the exact value on that, right? So we will divide that by 1K and we'll get the exact value that we are actually reading. So this is more or less how the ADC work, and that someone wants to implement a system or a PLC that has an ADC for reading signals. This is how from the programming point of view, how it works. Well, since we are looking to ways to attack this, right, I'm going to introduce what aliasing is. We have probably studied this on high school or on the university. The aliasing is when there's some distortion on the signal, but not because the signal is wrong, because we are not reading it in the right way, right? So if we go back to the image that I showed before, here we can see that we are sampling the input signal. We are not doing it right. So we have the Nyquist rule that he managed to say that at least we need to sample a signal 2 times the frequency the signal has, right? So if the signal has a 1 Hz frequency, at least we should sample at 2 Hz, because otherwise we will gonna get nothing. But well, even though 2 times the frequency is not enough for all type of signals, because if the signal is too complex or is modulated or something, even though you sample twice at the double of the frequency of the signal, you won't be getting enough information of the signal. So it has to be slightly higher. So for example, here we can see that if we are doing it wrong, we are not actually getting any close to the signal itself. So this is how it looks like when we're doing sampling, right? This flow shows we are sampling at different frequencies. So we have the sine wave that we want to actually sample, but we are doing it wrong. So we are getting things that are completely they are not accurate enough for the signal. So we start increasing the frequency of sampling, and slightly getting closer and closer till it finally goes to the right signal. That would be that we have at least the right frequency. So this, as we can see, if we don't match the signal we want to sample with the frequency, or the sampling frequency, we can get into this aliasing problem, which will obviously confuse the system, right? So for avoiding this, this is the implementations usually use the anti-aliasing filters, which basically does is that if we are sampling at 1K hertz, we need to put an anti-aliasing filter that blocks all the frequencies beyond 100 hertz to be sure that we are not sampling something above the Nyquist rule, right? So our input system would just block with the help of the aliasing filter, would block all the all the frequencies beyond that range. This is, as we security researchers and security people, we all know that in any system, there is the rule of you have to validate the inputs, right? If you are in a web app, you have to validate any input from the user. No matter what, you have to validate it. So this is more or less the same for ADCs in a pure electrical engineering point of view. So you also have to validate the inputs, because as we will see in the future, in later presentations, it can lead to problems with ADCs. So why is this thing important, right? I mean, currently we know that we can hack into PLCs, we can take control of PLCs. There are conferences in Black Hat and all the conferences around the world that show you how to compromise a PLC, a SCADA system, or whatever. So right now we are in a point that the cyber-physical threats are getting more important, which means that what can happen if we compromise this PLC, or we compromise a lighting system? Could we put a bulb to burn, or could we potentially, like this happen, like a exploded power plant or turbine or something like that, right? Because okay, you have done a great job, you've compromised a PLC, but what can happen? It's just more like you can do, you can annoy the operators, like trying to switch some lights or do some annoying things, or you can go forward and you can cause real damage, right? So this is the key point of the talk here. Well, this is more some simple view of how a control system works that probably most of you already know. We have the physical process. That could be a boiler, could be a spinning motor, or anything else. We have sensors that helps the system know in which state the boiler is, or in which state the physical process is, because we need to know it. We need to know exactly what is happening there in order to actuate, to increase the temperature, to decrease the temperature, to stop the process because it's gone out of control. We have to really know what is going on there. Well, once the system reads this, it produces an action, and that action is going back to the physical process. So where we are focusing with this talk is exactly here on the sensors part, which is exactly the place where the ADCs are used. Okay, because for actuators we have the DACs, the DAC, which is the opposite of an ADC, but it's out of this talk. So the main idea behind this talk on how you can fool an ADC is not how you can fool an ADC. Actually, it's how you can fool the system using an ADC, right? Because the ADC is a passive component that you could more or less try to play with it, but the point is trying to fool actually the system behind it that is using the ADC. So in a critical infrastructure, I mean, in a ICS system, in a SCADA system, in an industrial control system, we can have like this type of deployment, right? We have the control PLC, which is the one that reads the data and then adjust the signals to, let's say, if we have a spinning motor to increase the speed, decrease the speed, or whatever, right? So we have an analog signal there, and an analog signal you can only have one analog signal there. So once this voltage or this signal that goes to the motor or to the heating system to increase or decrease the voltage. The SCADA system usually have the monitoring PLCs that helps the system check whether that is actually going well, right? Because you can have the PLC, you can have everything in place, but someone knows to know is everything okay? All the voltages in the system are okay, and sometimes even if you hack into a PLC and you're able to change things, like I could stop this motor, I could put it to work when it's not meant to be working, or increase the temperature. Those are things that we already know can happen. But if the design the design of the system is properly well done, we have the safety control PLCs and the monitoring system that will raise alarms. So what it will cause that someone in the control room will notice that and will say, oh, something is extremely wrong with the motor. We're going to turn off that PLC because something is going to happen, or they can act, right? So the point here is, could be possible for an attacker to actually make the safety control room think that everything is okay when it's actually not, or the opposite, think that everything is wrong when it's actually okay. So the focus of this talk is trying to fool the ADCs, or trying to make the systems that read data from ADCs to think things that are not real, right? And so we have this situation where the safety system, the safety PLC, the monitoring PLC thinks that everything is fine, but we are actually turning on the actuator, right? We're increasing the temperature in the boiler, or decreasing it, or making the motor spin at very weird speed so they can actually be broke. So in this talk, we have analyzed 6 different devices. These are all Sigma Delta ADCs, except well, this is a real PLC that we don't actually know what is inside because there is no documentation on it. Maybe it's a SAR ADC, but I think it doesn't really matter here. So, okay, we want to attack this way, okay? We want to do this. Which are the actual attack vectors for this? So one may think like, okay, you have the SPI interface, so let's try to fuzz it or do something fancy on that. But since it's controlled by the host, I think there's not much to do there, because if you're already having control of the host, you could actually do other stuff. So we're actually going to focus on how to attack the ADCs from 2 ways. It's purely from the analog world. So we are going to attack them through the amplitude and frequency. So we're going to start studying a little bit how on the amplitude world, right? This is a setup that could be in any PLC. We have the ADC, which in this example we are monitoring three different channels. So we have 3 different input signals there. And we have the fourth channel that we are monitoring on the channel 7 that is controlled by an attacker, right? So the whole system is doing what it has to do. It has to go to the ADC, read the data, and using that data make any action, right? So what we're gonna do is we play a bit with the amplitude. So in all the data sets where you have this table where it shows you which are the valid ranges of voltage that you can use with different channels. So here we're gonna play on the negative side of the to see what actually happens, right? To an ADC when you supply something that normally is not used to be there or shouldn't be there, right? So we have recorded. We use 2 different ADCs. This is the AD7706, and then we use another ADC which is integrated in a AVR and an Atmel device. So in this video, we can see that here all the channels. I don't know where I can point here. What? Here. Let's see. Without pointer, it's a bit complicated. So. Okay, as you can see, what we did was actually plug with the power supply, we generated different amplitudes. And at the beginning, if we go to, I can't really point, at the top of the here, it's before injecting any voltage, right? So we have 4 channels. We have 0, 0, 0, which actually is the amplitude. Okay, thanks. Which is the below. Which is the amplitude that we are using, and the last value is the reference level of the setup we have here. So if we go, now that we come here, at this point, as you can see, the 3rd channel is the one connected to the power supply. Okay, what we did was actually reverse the polarity, right? So we can generate a negative signal even though the power supply generates positive signal, but we reverse the order. So we're generating negative signal And here we're starting to increase a bit. So these are like 30 millivolts. And we see that since this is supposed to only output positive values, it gets like subtracted, right? So this is okay. The other two channels are fine. But once we reach the 300 millivolts level, the negative 300 millivolts level, we see that in the other two channels, we are getting readings that they are not actually there. So using the funny thing with it is that using just one channel, we were able to affect we were able to affect the readings from other channels. So that's one of the attacks that you can have with these ADCs. And on this is actually it's only plain. It's a different ADCs with one integrated in one board. So here we have the 4 or 5 channels are connected. The 5 volts is the reference, and then when we start injecting the negative value, we see that there are some weird readings on different channels. For example, the one that was reading 3.3, that was actually the reference level from standard diagram. We were able to affect it. So instead of reading 3.3, which would be the actual value, we were able to change the reading of the ADC, just attacking a completely different channel. So we didn't really need to access it. So as a summary of how to attack one ADC from the amplitude side, what we did was to force the voltage into negative values. So what we did basically was trying to go through the boundaries of the system so we can see what happened in there. So we saw that with the ADC that we tested, some weird things can happen. So for example, if someone is reading a temperature and suddenly it goes to the maximum level, it will raise an alarm in the system and some action will take place that didn't need to be taken because the actual signal on the channel is okay. We are only affecting how the ADC reads that information from the world. So, as I said, just owning one simple channel will render the other channels or other signals can be affected. So, with the study bit how the amplitude works, how we can attack a system from the amplitude, and now we are going to check how it works with the frequency, right? Which is the next step. So, and I'm gonna talk a bit about delta sigma ADCs, which can be a bit boring. So I will try to go very fast through it and just highlight the very thing. So delta sigma, one of the properties of the delta sigma ADCs is that they use oversampling of the signal. So they are one of the marketing points of the ADCs is that we are oversampling the signal too much, and that you don't really need as strict anti-aliasing filters. So we go back to the introduction. So since we are sampling probably 20 times the frequency that you are going to actually read, you can't relax that requirement. So you can have a more broad bandwidth of no rejection part on the ADC. So, and this is actually how it's advertised on the market, right? Since the sampling frequency is very far from for the actual spectrum you want to see, you don't need to do as a strict rejection of frequencies. So to achieve this, the delta sigma has different parts. I will go a bit faster through this. They had a modulator that with the signal and do some comparison. That's the part that does oversampling very fast to get a very precise information of the impulse signal. Then they implement a digital low pass filter that is interesting and will be subject of what we'll see afterwards. That this low pass filter is a filter that cuts some frequencies, and this is more or less how it looks from a functional point of view. You get the input signal, it goes through the signal is read, and at the end of the day you get a bit and it goes back, it's feedback to the input, to trying to get more or less what we see here, which is how the delta sigma works. You have the input signal, and then the output stream of the DAC would be down here. And another function block of how this works. So, okay, forget about it. It's a bit boring. And this is actually the functional diagram of the delta sigma ADC that we are going to attack, the AD7706. So we can see here the modulator and the digital filter, and this is the PGA, which is the programmable gain amplitude that it's offered. It's like a feature of the ADC that if you, for example, are trying to sample very weak signals, you could actually like amplify the signal. I mean, it has a number of gains that you can set, and it helps you get a better resolution of the signal, because it amplifies a bit the signal, and well, it changes the cutoff of the different filters. So it's tiny, and it's handy, and we will study that later. So this is the setup we have for this attack. So we use the picoscope to generate signals. We are here interfacing with the ADC, and here we have the AD7706 interfacing with that. And this is more or less how we perform the attack. Well, this is part not actually attack. This is, we are trying to identify what would happen to the system if we start playing with the frequency, right? So we are going to start sampling from 0 to several megahertz frequency of the input signal. We're going to record it, do some statistics on that, and try to see if everything is okay or there is any weird thing happening. So this is what I talked before, the gain here. So we're going to focus on this frequency, because this is part of the how I call it, the filter. So the frequency here are frequencies that when you change the gain, these are the corners of the filter, the points where they let pass an attenuated noise, as should be. So in the corners, so you have the filter that blocks exactly a huge amount of signal, and then you have, well, the filters are not ideal. So you have a band that it completely blocks, and then you have a point where you can get an attenuated noise. All right, so just have in mind that we should get at these points an attenuated noise, and we will see what happened afterwards. So once we increase the gain to 2, to get more accuracy of the signal, the first corner moves slightly to the right, and instead of being the 32, the 32 is now 76K. So it means that all the frequencies in this range should be completely blocked, because it's on the side of the filter that should be completely blocked. All right. So more or less what it says there. So this is explaining a bit what I was talking before. We have the filter blocking areas here, and if we have gain 1, so we see here that the ADC would pass some input signal to the output being unattenuated, and then we have the other one for the multiple of that. I mean, the numbers are different because we are not using the same clock as the datasheet. It's actually 2 megahertz clock, and when we set that to gain 2, what happens is that, as I said, the first corner corresponds to the next one, and the 31250 should be completely blocked. So on this demo, we are going to show how this works. So we have basically on this part is the picoscope interface, and this is what we are actually reading, sampling with the Arduino, right? So we are increasing the frequencies. These are frequencies that should be okay with ADC. So we're generating them and we are reading them perfectly fine. We have 3 hertz, and we are also supplying. It's kind of very well read here, but we are supplying an amplitude of 1 volt. So we have here, it's offsetted also to be able to get it right. So we're getting here the signal, and once we get off the filter, we start getting attenuated signal here, and what we get here is like we're out of the filter, or we're already out of the frequencies that are supposed to be sampled by the ADC. So this is okay. We are not having any aliasing problem, so we are getting noise, or we're getting we are getting anything. As we can see, we started increasing the frequencies, and we get. I'm gonna say a bit of a spoiler. The frequency is the 31250. So as we can see, these are frequencies that should be completely blocked by the system. All right. So where we are actually seeing here is that once we get closer to the actual value here, we will start seeing some weird things. Okay, this will be okay because it's noise and it's perfectly fine. We are able to control it. But when we reach the magic number of 31250, we see that the ADC is actually reading a completely different signal, right? It's a half-hertz signal that is not in the system, and we are generating, the input signal is a 31K signal. So this is a very important thing, right? Because it's like we are generating a signal that would cause a problem to an actuator, but the system PLC would think that it's reading something completely different. So we managed to, using the frequency, to make the safety critical system think that things are okay or not okay, because if the monitoring system is expecting this type of signal or any other value that we can generate through here, it will read it and it will say, okay, it's totally fine, but we were injecting something completely different. So this is what happens here. It's more or less the whole sweep between the frequencies around that specific point. And there is also a video here. So also one thing that happens here is that in the data sheet it says that in this point should be an attenuating noise, right? So maybe it would be okay if we get some noise on that point that is not attenuated, but the thing is that we are getting exactly the same signal that we are putting in the input, but at a different frequency. So it's a very weird thing that happens with this ADC. And what should happen at these frequencies is that it should be completely blocked. So, and the video shows how is the output of the ADC once we reach to the 31250 signal. So we are getting closer. That's okay. That's noise. That should be completely fine for the system. But once we are getting closer and closer, we start seeing that we approach the input voltage that we supplied, and we are almost there. So we're starting to see exactly the signal that we got, and then we go back to the noise again. Okay, let's pass this. And okay, so this is a pure theoretical point of view. So how this would work how could we generate signals that matches what the simple ADC is working? Because I mean, okay, we were able to inject a signal and get something from the output, but this would only work if we managed to let the PLC, the safety PLC system, see exactly what he thinks has to be in the line. Because if for example, he's looking for that square signal and we inject something, a sine wave, it will fail. And the monitoring system will realize that something is wrong on the line. So as an example here, we are inputting different types of signals. And as you can see, they are not exactly the same because we're injecting them as at the 31K kilohertz, and the output is half a hertz. But okay, you can see that with the editor of the picoscope, we can generate any type of signal. So the thing that is happening here is the ADC is not blocking at all the signal that should be blocked, and it's actually getting the signal as it and multiplying it by 2 because we are in the game too. So this is a weird scenario. So here we kept playing with the signals. As you can see, it's not exactly the same because it's sampled and there are some minor changes on the readings. So this is what happened for the AD7706. So we started thinking, okay, what is going on here? I mean, why is this happening like this, right? So we thought about maybe in the filter there is some areas where there are no noise transitions, but at the end of the day, we have no idea what happened, right? So that was our first conclusion. We have a clue. We kept thinking, and no idea. We didn't come up with any possible explanation until Alexander, thinking about it, he said, okay, maybe it's a possible integer overflow. I mean, this is our speculation, right? Because we haven't built an ADC ever. We don't know exactly how these sigma delta things are made from the BSDL point of view, but these are speculations. So Alexander started working and well, he got how the filter is implemented somewhere. He got the code, and we started working on creating a simulation on Python, right? So we created the signal. So this is the how the filter would work. This is fine. The total fine filter where we input the signal and we get noise. So there is nothing there. It's just noise. So in order to prove that, or to test whether what would happen if we put an integer overflow on the filter implementation, this is the Python code. So we created this a specific overflow plus. So if the sum goes over a limit, it gets overflowed on the output. So at the beginning, we don't know what is going to happen out of this, but interestingly, it is more or less the same what we got on the ADC. So we have this very high frequency signal, and on the output, after introducing the integer overflow on the filter calculations, we got the much lower frequency signal. So maybe this is just a plausible explanation that just was fun to try. So we also went one step ahead, and we did some decapping of the chip thanks to our shuttle lab to see whether we could see that it was a microprocessor or something that could validate or a software, right, or the integer overflow. But from here, we can't see much, and well, this is the clock generation, the voltages, and this is some CMOS logic, but it doesn't look like the microprocessor. So maybe we were completely wrong. Or maybe, well, you can also introduce bugs. If you are programming on very low, you could possibly do some bad calculations and get some integer overflows, but who knows? The next device is well, that was entirely with the AD7706, and how we studied that, and we found frequencies that someone could hide what he's actually doing, right? So in this, when using this PLC, which is an actual PLC, we don't know exactly which type of ADC it has. We created like a setup, right? Like a real power plant setup where we have the PLC, the turbine here that is generating power for the nuclear plant, and the controlling room, the control room that is monitoring what is going on there. So, okay, if we have noise, this would make a noise, but we'll try to see it. So we basically doing this same playing with the frequencies. It's a bit different than the one before, but I will show you how it looks like. Right now we are generating the signal in a right way. You don't see anything weird there. The PLC built the line and everything is fine. But in a moment you will start. If you see the motor, you will see that it starts making weird moves. So that's when we started introducing that. You see that it's making weird moves. That means that we are not driving the motor in the right way. We are inputting weird frequencies into the speed. So it means that, well, if this is a huge turbine or a huge motor, you could actually break it because you are causing lots of vibrations on everything around it. So the important thing is that the safety PLC system still thinks that everything is fine, that you're supplying the continuous 3.6 volt, right? So this is the code we used to generate this. Basically, the way, as I said before, the main thing we want to do is to try to fool the host of the ADC, right? So, okay, we can fool the ADC, but the point is to fool the system that is using the ADC, trying to make things that are seeing things that are not there. So we basically here, we put the line to the right value for a certain amount of time, and after that time, we introduce this fast switching on and off the driving the motor very fast with a high frequency. So that was the actual movement that you saw are actually produced by that amount, right, of code. And as you saw from the video, the actual readings of the value is totally fine. It doesn't really detect the ups and downs of the signal. So otherwise, it should be attenuate or indicate that something is wrong with the line. So the waveform that we generated is more or less like this. So why it works? So why this works is because the ADCs, well, not ADCs, the way the programmers, or where I also worked a few years ago with this type of systems, usually do is you read a value and then you start doing something else, right? You are not continuously monitoring the system because you say, okay, I'm going to monitor this, just do it once per second or every 2 seconds, something like that. You probably read like during 100 milliseconds, you read a few values, you take the average to remove some outliers that can cause some quantification problems, and everything is fine, and then you go to sleep. But following this approach, what is happening is that, of course, while you are sleeping, the system can be changing. So that's exactly what happened on this PLC. It's reading the signal, but it does this type of read and sleep. So during the times the PLC is actually sleeping, we can inject signals very fast and cause weird problems that are like the one that you saw. We could use that signal. This is another example of what we could use, right? On the bottom is the time that the software is actually reading, and during the other time is doing something else. It's probably not sleeping, but it's doing calculations or maybe actually sleeping. I actually did that quite a few in the past. So, well, that's also with the PLC system, and we also studied more ADCs, right? We had 6. We studied this one, which you can see. This is the same procedure we did before. We studied from 0 to several megahertz. This takes, because we are using Python and blah blah blah, this takes several weeks to get. It's not something that you calculate in a few minutes. So I think it took like a month per ADC to get the whole frequency range. So as we can see here, this is all these frequencies. You're getting some unattenuated signal, but it's not enough. This is the area where we're getting the right signal, the input signal, and the one that we want to read. But we keep increasing the frequency. We start getting points where, okay, you get some noise. Did you find this area, which is more or less the same input and the same amplitude of the input, but in this case, we don't get the same input signal as we happen with the 87706. Here we get a noise, right? So we get an attenuated noise. Could this be used for an attacker? We have to study it more because it depends on how much you can control that noise. If that noise in a more or less statistical value, you can get to a certain level, maybe in some cases work. But it's not like as it's just in the other one that exactly replicates your signal at a different frequency. Well, this is a magnified part of the beginning. We also studied this other ADC, which more or less performs the same. And this is funny because here this both seem similar, but this one is actually in this area where we have the unattenuated, well, the same level of the amplitude of the input. Even though we play with different waveforms, we were getting always the sine wave. No matter what input we got, it was always the sine wave, but we couldn't control it. So this would work if the safety system is expecting exactly that waveform and is expecting the same and that frequency. You could fool the PLC with this ADC, but it's more complicated than the first one that we saw. And this always someone does the things right. So this is how it should look like when you have properly implemented anti-aliasing filter and everything. That you get the signal at the beginning. This is a magnified view at the beginning. So you get the signal on the ranges that you have to get a signal, but beyond that, you don't get anything else. It doesn't matter which frequency you input. So with this ADC, everything should be fine. And then we also tested the Cypress PES OC5, which is a SOC which has a FPGA allows you to write some logic on it, and it was very fun because we found this output that we don't know what it is. So it's just, what is that? So at some frequencies, so how it looks like is for, let's say, 50 Ks, you're getting this value. 50 Ks plus 1 Hertz, you're getting this value. 50 Ks plus 2 Hertz, you're getting another value. So it's extremely weird response to the frequencies. And of course, this part here is also very interesting, right? Because we have no clue. We have to do more research on this, and we'll see what is going on. But this is a magnification again of the beginning. So this is the weird looking output you get, and this is a summary table of how easy, complicated, or impossible it is to fool the system using these ADCs. And as a final thought, the recommendation here is always like validate your input the same way we do with web browsers, with mobile apps. Anything that get an input from the outside should be validated. It's the same thing. So the only thing is that we probably there is not much attention on the pure electrical part of the systems. So even though on some data sets they recommend using anti-aliasing filters, sometimes they are too relaxed that allow you to put like 50K bandwidth. So if you're using a system with a narrow bandwidth, try to put an anti-aliasing filter for that part. And well, that's it. So any question or anything? Thank you.
So you mentioned that it could be this integer overflow. So you seem to think that it is a digital problem, in fact. Or is it an electrical problem, like some parasitic currents or interference, or?
It is a digital problem that causes the thing, because at the end of the day, most of these systems, some of them has a microprocessor inside that drives the whole reading, the whole outputting, because they have to also convert to SPI. And as we know, if you have software, you can update, you can fix, you can do everything instead of changing the whole thing with VHDL, which is more complicated and but in fact, yes, if it's actually integer overflow, which could be, I don't know, if someone has more experience with that, we are really happy to hear. But yeah, it's a totally inter-digital thing.
How much of the behavior do you think is down to anomalies or weaknesses, and how much down to just normal behavior of Z transform type?
Sorry, I didn't get the question.
How much behavior is maybe anomalous or due to weaknesses in implementation, like an overflow, or how much do you think is just down to the normal characteristics of taking something into the Z transform and out of the digital filtering?
The thing is, if even in the AD7706, if you put the proper anti-aliasing filter, this attack should be stopped. It's like if you got the database, if the database is okay, but if you use it wrong, you're gonna get SQL injections, right? So it's more or less the same. The ADC is what it is. Maybe that's a feature that can be changed, but if you properly narrow the bandwidth that you are using, you won't be getting these problems. This problem arises because for the delta sigma ADCs, the marketing point is like you don't need as a strict anti-aliasing filter because it's oversampling. So if you are sampling at 10 times or 20 times the frequency you're reading, you don't need that much that. But we've shown that if you go above that limit, even below the anti-aliasing filter start cutting off the frequencies, there can be problems. And I mean, and that's one thing, one of the questions you asked, and the other one is whether that is a problem of the ADC. I think if the same data set shows you that at gain 2, the frequency we are using should be blocked, it's an implementation issue of or the data set is wrong. So something is missing there, or the data set is not properly written. That could be also be true, or they are doing wrong in whatever thing they are doing. Mainly because also I don't know, this is just speculation, but they don't expect anyone trying to do these type of things, right? It's like when the early days, no one did anything on the software. No one validated anything. You just get everything on the IOTLs of the kernel. You assume that the pointers you were getting were kernel space, but what happens if you're using user space pointers, right? More or less the same. Things are there, they could be broken, so you have to validate whatever goes in there and make sure that it matches what it has to be. Thank you. Sure.